Okay, now we're going to look at a theorem that will probably remind you a lot of something we've seen before. So this is about the interaction between relative complement and union. And the way it works is that it does distribute. So if I do A relative complement a union, then it does distribute, but the union becomes an intersection. So what does this remind you of? Hopefully it reminds you of DeMorgan's law from logic, where a not can distribute over an or, and when it distributes, the or flips and becomes an and. So this is a very similar kind of thing. And in fact, this is also called DeMorgan's law. This is what we're looking at, is Theorem 34, Part 2. This is also called DeMorgan's law, but it's the set theoretic version of DeMorgan's law. One thing to be aware of about the difference between this and the logical version of DeMorgan's law is that this is an equality between two things. So here we're saying if you form this thing versus if you form this thing, those are the same thing. They would refer to the same object. On the other hand, the logical DeMorgan's law, the original one here, was not an equality. It's a logical equivalence between two propositions. So it's saying to say this is equivalent to saying this. These are like assertions, and we're saying that they are the same assertion. So before we look at the proof of this, I just want to make it kind of intuitive in some way. So there are three sets involved, A, B, and C. So let's imagine those as blobs, kind of with a Venn diagram. Maybe like this. So this one is A, this one is B, and this one is C. So what I mean by this is, imagine that A is a bag of stuff, but I'm depicting that as all the stuff is just points on this, pixels on your screen. Everything inside here, those are all elements of A. So like this pixel, if this were one pixel, that pixel is an element of A. So is that, so is that, so is that, and so on. All the pixels on your screen here are elements of B, and all the ones here are elements of C. Things here are in A and B. Things here are in both A and C. Here they're in A, B, and C. Out here, things are in none of them, not in A, not in B, and not in C. Okay, so then what's B union C? B union C, that would be the things that are like this. That's B union C, right? Everything that's in both B, everything that's either in B or C or in both, right? Some of the things in B union C are only in B, some are only in C, and some are in both. What about A without B? By the way, that's how I read this backslash symbol, the set minus symbol. I read it as without. So, that's a good way to think about it, right? It's the things in A that are not in B. So I read this as A without B. A delete B. So what does A without B look like? Actually, let me keep the colors. So B union C can be like that. And then let's do A without B in green. So A without B would be everything that's in A that is also not in B. So it would consist of these things. So basically take A and then let B bite a chunk out of it. And then what you're left with is A without B. And then A without C, let's do that one in red. That would be everything that's in A but with C taking a chunk out of it. So in A but not in C. So then in white, let's do this entire left side. A without the blue stuff. So if I take A and I delete the blue stuff, then what do I get? I get this part. All the things that are in A, but not in the union of B and C, which is the blue stuff. So just this here. So that's the left-hand side. Is that equal to the right-hand side? Is that equal to what I would get if I intersected the green and the red? It looks like it, right? If you take the green is Let me use the pointer here. The green is this part. Let me outline it. This is the green, is this part. And then the red is this part. And if I intersect them, take the things that are both in the green and in the red, then I get this part. And that's the same as the white. So this is not a proof at all. It's just a picture, but it suggests that this, why this might be true. Okay, and this one is not proven in the notes. Part 1 is done in the notes. Part 2 is left as an exercise, so I'm doing that in the lecture just to give you something different in the lecture versus the notes. Okay, so we need to prove an equality. That means we need to prove, we have a couple of options. We could use Axiom 8, or we could use Theorem 10. I'm going to focus on using Theorem 10, even though I think Axiom 8 might work here. So I'll use Theorem 10, just because that's something that will be more commonly useful in the future, so better to observe how that works. So that means the whole proof will split into two portions, the inclusion in this direction and the inclusion in the other direction. So starting from left to right, consider any z in the left-hand side. Now my goal is to show that z is in the right-hand side. So if I get stuck at any point, then maybe I'll section off a zone for my scratch work and then start working out what my goal is and trying to work backwards from that. But I'm not stuck yet. There's a lot to unpack here. So already there's something to unpack here with z being in here. This is something that I can unwind and figure out what this really says. So for that, I need to use the definition of relative complement. For z to be in there is for z to be in here and not in here. So I'm using definition 33 here and axiom 5. To be in a relative complement is to have this condition hold for you. The condition here, why is that so hard to highlight? This condition here. The thing between the bar and the curly brace. So for z to be in a relative complement is for it to be in the left-hand thing and not in the right-hand thing. So then z is in A, and z is not in B union C. Now, this is interesting. How do I break down z is not in B union C? I know how to break down z is in B union C, so how do I break down not in? Well, okay, now let's put down a scratch work zone. So z not in B union C, that's the same as saying it's not the case that z is in B union C, right? And I can break down z in B union C. That says z in B or z in C. Using the definition here, the definition of union. So what I've got is it's not the case that z is in B or z is in C. Okay, but I have DeMorgan's law from logic for propositions that says that a not can distribute like this. So this tells me z is not in B and z is not in C. And the or becomes an and. And of course I'm allowed to use that, and I don't need to say what I'm using when I use that because that's just from logic. We sort of assume that all of logic is available as we were doing set theory. Okay, so now I know what to say next. Then it's not the case that z is in B or z is in C. So z is not in B and z is not in C. And this is by the logical DeMorgan's law, but I do not necessarily need to reference that. What you do need to reference is the stuff here in this reference document, starting from axiom 1 onward. The logic stuff, we typically do not reference that. So z is in B, not in B, and z is not in C. Okay, now I think I've broken things down as much as possible. now I should focus on my goal. My goal is to prove that z is in this right-hand side. So let me clear this area. So my goal is to prove that z is in here. A without B intersect A without C. Which means my goal, now using the definition of intersection, my goal is to prove z is in here and z is in here. So I sort of have two goals. My goal is to prove this and to prove this. And if I break this one down, that means I want to prove z is in A and z is not in B. And if I break this one down, that means I want to prove z is in A and z is not in C. Okay, so I basically have four things to prove. Z is in A, Z is not in B, Z is in A, Z is not in C. Okay, but I repeated myself. I have three things to prove. My goal is to prove Z is in A, Z is not in B, and Z is not in C. And now I can look back at what I have. Hey, I've already reached there. Z is in A, Z is not in B, and Z is not in C. So all I have to do is put the pieces back together and work my way back up my chain of goals here. So let's see, since Z is in A and Z is not in B, Z is in A without B. Since Z is in A and Z is not in C, Z is in A without C. Therefore, so now that I have these two, Z is in A without B, Z is in A without C, therefore Z is in the intersection of those two. And that's it for the forward inclusion. Now for the other inclusion. So consider any z in the right-hand side, and then try to show it's in the left side. Okay, and let me clear this stuff out here. So now, let me unpack this as much as possible, just like last time, and then I'll focus on my goal afterwards. So then, z is in this intersection, so z is in the first of the two things being intersected, and z is in the second. So I'm using the definition of intersection to do that. Now I have to use the definition of relative complement to break these down. So using definition 33 here, we have z is in A and z is not in B. That's what this breaks down into. And z is in A and z is not in C. That's what this breaks down into. Therefore, well, I'm actually not sure what to say next. It seems like I've broken things down as much as possible. So let me focus on my goal, which by now I have forgotten what it is. Going back, I'm trying to show z is in the left-hand side, which is A without B union C. Okay. My goal is to show z is in A without B union C, which breaks down into z is in A and z is not in B union C. So I have two things to prove, this and this. This one is interesting. This one is basically saying it's not the case that z is in B union C, right? Which means I need to prove it's not the case that z is in B or z is in C. And all of this is looking a lot like what we did before, right? That's because all the deductions we're making pretty much go both ways. They're really double arrows, not one-way arrows. So this whole proof could have been maybe made more elegant or quick if we used axiom 8 rather than theorem 10. But I'm insisting on using theorem 10 just to show an example. Yeah, so again, we can use DeMorgan's law here and be like, well, this is the same as proving this, but with the or flipped to being an and. Like that. So now my goal is to prove three things. These two, so that I get this and I also had this goal from earlier. And look what I have, those exact three things, right? So now I just have to work my way back up what I'm thinking here. So therefore, since z is not in B and z is not in C, we have it's not the case that z is in B or z is in C. So that's using the logical DeMorgan's law. It's using this derived rule here. And then since, so what's written here is z in B union C, except it's inside a not, right? So z is not in B union C. Since z is in A, that was up here, and we said it twice, in fact. Since z is in A and z is not in B union C, z is in A without B union C.